Sup guys? Today we have another math competition problem. That's fucking cool. Okay, so what do we have here? We have uh, a series an, all positive integers, and we have a recursive function with this formula. So the next number in the series is equal to the last one plus floor of the square root of an plus roof of square root of an. So what these two mean, if you don't know, you can skip this part otherwise. So floor means basically that if it's a non-integer, you take the greatest integer that's less than that. So if you have 1.5, it's 1. If you have 2.9, it's 2. Yeah. You just put it down to the first integer, and the opposite holds for this one. So you just roof it instead. You take it to the smallest larger integer. So the same. 1.5 becomes 2 and 2.9 becomes 3. So yeah. Um, and we're supposed to find a polynomial p such that for all n greater than 1, we have that the polynomial of n is an. So we're supposed to find a polynomial that satisfies this series, basically. Um, and here I've written down a quick 1 to the power of 2 is 1, 2 to the power of 2 is 4, and so on. We'll use that later. So what should we do? This problem seems pretty ugly at first. Um, so I'd say just try. Just honestly, just try. So if we just set the first integer, let's say a 0, if we set that to be 0, then everything just, then we have, okay, we have 0, the square root of 0 is 0, floor, that is 0, 0, okay, so it just continues on. All the series, all the integers in the series are just 0, so that won't work. Scratch that, but if we instead try maybe 1, seems like the best option. What do we have then? So, okay, what is a1 then? A1 is then, okay, so we have 1 plus square root of 1, that's 1, floor of that's just 1, and plus 1. So, okay, so we have 3. Okay, and what is a2 then? A2 is then 3 plus the square root of 3 is between 1 and 2, right? Because 3 is between 4 and 1. So we have that the floor of the square root is 1 and the roof of the square root is 2. So we have 3 plus 1 plus 2. So that's 6. And then a3 should be then equal to 6 plus, okay, the square root of 6, because 6 is between 4 and 9, the square root of 6 should be between 2 and 3, right? So the floor of square root of 6 is 2 and the roof of square root of 6 is 3. So we have 6 plus 2 plus 3, that's 11. And you get the pattern, I can just give you that a4 is 11 plus 3, yeah, it's 18. Exactly. And then we can write down a5 also. a5 should then be equal to 18 plus 4 plus 5, so that's 27. Yeah. Okay, so what we're planning to do now basically is that for all n, sorry, it should be less, sorry, greater or equal to 1, we have that. So basically we can forget about this part. We're just supposed to find a polynomial that satisfies this. So what is this polynomial? If you don't see it straight up, we can start with looking at the differences between each of the terms. So we have between 1 and 2, it's 3. Between 2 and 3, it's 5. And then it's 7 is the difference there, and 9 is the difference. So what we want is a polynomial wherein the difference between each term, that value of the integer, inputs in the function should be another polynomial, right? 3, 5, 7, 9. What does that look like? Well, it obviously just looks like 2x plus 1, right? If we consider it, it depends a bit on how you like phrase it. But if you think about this, think about the next minus the current, then we have that the function should be 2x plus 1 or 2n plus 1. Both work. So what we want is we want a polynomial that satisfies the equation p n plus 1 minus p of n is equal to 2n plus 1. How do we solve this? Well, what we have is that the difference between two consecutive values is always supposed to be this function. So we can say that this has to be satisfied for all n. You write it this way. That means for all n. So what is this polynomial? We can first ask, what grade is this polynomial? One might expect that the kind of similarly to a derivative, that the derivative of a two-grade polynomial is a first-grade polynomial. And that is absolutely correct. So basically all we have to do now is just say that p is some general polynomial. We'll just call
p of n to be equal to a n squared plus b n plus c.
And then we just plug in n plus 1, and then minus this. And we find out what a and b and c are for this to be true for all n's. So if we just plug that in there, then we get that
a n squared plus 2an plus a plus bn plus b, and then we have plus c minus a n squared plus minus bn minus c. And this is
so we can just remove some things. So these two cancel out, these two cancel out, and these two also cancel out. So we have left is 2an plus a plus b is supposed to be equal to 2n plus 1 for all n. And if this is supposed to be true for all n, this left-hand side should be just this expression. So we can firstly, if this is supposed to be true for all n, then we can just see that, okay, 2n has to be equal to 2an for all n. So we just know that a is equal to 1. And also a plus b has to be equal to 1. So, and because a is 1, then we know that b is 0. So our function that we have now arrived at that p of n is therefore equal to n squared, and then no factor for the n. But we still don't know what c is. So to do this, we just plug it into there. So okay, so we know that when n is 1, then it's supposed to be 3. So 1 squared, that's 1, and so plus c is supposed to be equal to 3, so c must be equal to 2. So we have our polynomial n squared plus 2, which in hindsight is really obvious because this is just 1 plus 2, this is 4 plus 2, this is 9 plus 2, this is 16, 25. Yeah, you get the point. Yes. So now, we have our polynomial, but we have a bit more things to do. So what we have to do now, basically, is just prove that p
n plus 1 is equal to p n plus floor of square root of p of n plus roof of square root of p of n.
and because we know that what p of n is in terms of n, so we can just write this out instead. So we get that
This is equivalent to n2 plus 2n plus 3 is equal to n squared plus 2 plus floor of square root of n squared plus 2 plus roof of square root of n2 plus 2. And
as we can see, we can cancel out the n squared and remove this, so that this becomes a 1. So that 2n plus 1 is supposed to be equal to this thing. So now we have to kind of standardize or mathematically write out really what a floor function is. So basically what we have is that if floor of n is equal to x, that is equivalent to that x is less than or equal to n, which is less than x plus 1. Because if n is anywhere between x and x plus 1, then floor of it is x. And it also includes if n is equal to x, then the floor of the function or the roof function does nothing. So, and we can write out the other case too. The roof of n is equal to x. What is that equivalent to? That means that x minus 1 is strictly less than n, which is less than or equal to x. Yes, because if it's equal to x minus 1, then the roof function of n is just x. So if it's anywhere in between, it goes upwards, but also including if it's actually equal to x. So what is then root floor of square root of n squared plus 2? I'm going to make a wild guess here and say that it's n. Because it kind of makes sense. Because if n is, say, 4, then we have 16 plus 2, that's 18. And since 18 is between 16 and 25, the square root is somewhere between 4 and 5. And then the floor of that is 4, right? So what we essentially get then is that, yeah, and also what is roof of n squared plus 2? That is also kind of obviously n plus 1, because n squared plus 2 is somewhere in between n plus 1 and n plus sorry, it's somewhere in between n squared and n plus 1 squared, because the difference between two squares is never less than 1, except when it's 0 and 1. But that doesn't matter. So basically what we have here is that if I claim that the floor of square root of n squared plus 2 is equal to n, that is then equivalent to saying that n is less than or equal to square root of n squared plus 2, which is then less than n plus 1. Then if we square all sides, all three sides, we get that, because everything is positive here, so we're not fucking anything up, n squared is less than or equal to n squared plus 2, which is strictly less than n squared plus 2n plus 1. See, these cancel out. So what we have left is just that 0 is strictly less than 2, which is less than 2n plus 1, which is true for all n greater or equal to 1. And that is within our domain for the problem. So that's great. And then we'll do the same for the roof and claim that that thing is equal to n plus 1, which is then equivalent to n being strictly less than the square root, sorry, n is less than the square root of 2, which is less than or equal to n plus 1. And you see that this is the exact same equation, and we end up. So if we plug this back there, we have that 2n plus 1 is equal to what was floor. I claim that to be n plus, and the roof, I claim that to be n plus 1. So that's plus n plus 1, which is equal to 2n plus 1. And we are done. Because it's the same. So we proved it. We have found a polynomial n squared plus 2, which satisfies the recursion formula that we had before, which is basically this one, for all n greater than 1. So we are done. Thank you. Bye.